All right, friends, this is Mr. Shagney coming at you with another lesson. So today we're going to be looking at common factors, and so we're going to be exploring what those look like with the three different activities that we're going to explore in class. And then your homework is going to ask you to use the stuff that we learned today to then solve problems. So it says 16.1 figures made of squares. How are the pairs of figures alike? How are they different? Well, if I'm looking at each one of these, I notice that, alike, how all the figures are alike. You could say something like each figure, each set has a blue figure and a yellow figure. You could say that each figure is made of small squares. And you could say that looking a little closely at these, the yellow figures are made up of 6, so that's 6 there, 6 squares here, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So yellow figures are made up of 6 squares, and blue figures are made up of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 squares. And then we can notice there are differences. So that's how they are alike. How are they different? So differences, so some make rectangles and some do not. The first pair, if we're looking here, this is the first pair. The first pair is made up of 2 rectangles. Um, and we could look at that, and then we could look at this one has an L shape, so you could say this. So this one has an L shape. It's the only one that makes a perfect L shape. This one's also the only one that has at least one. So this one has an L shape. This one, I mean, you could think of other things to say about them, and I know that I'm getting kind of off track here, but anything that you notice that they're different, you could write. So that's something that's possible there. But the big thing here is that we really want to talk about this number 6. So if this is made up of 6 squares and this is made up of 10 squares, I want you to notice, let's look at the height of this. The height of this is 2, and then the length or the base of this is 3. And we notice that 3 times 2 gives us 6. And then over here, this base, 1, 2, 3, 4, 5 is 2. And this height is, that's not 2, that's 5. This one's 5, and the height is 2, which makes a total of 10, right? Because we know that multiplying those should give us the area inside of the shape. And so we also know that these things are called factors. And so these numbers, when multiplied together, give us 10. These numbers, when multiplied together, give us 6. So if we're really looking at factors of 6 and 10, right, you can kind of see what works. So when the height goes here, right, 3 and 2 still work for 6. But this one, notice that it does not complete because you have 4 here, and then you have 3 here, and that's not necessarily a fact. Those are not factors of 10. And so here you have 2 as a base, and then 4, and then 4 times 2 is not a factor. This is not a factor of 6, right? So these 2 do not give you 6. And then here, this is 3 times 4, which is 12. That's also not a factor of 10. And then here, 4 by 2 still isn't that factor, right? Still is not a factor of that, so that's 1, 2, 3, 4, 5. Oh wait, that's 5 by 2, not 4 by 2. 5 by 2 is not a factor of 6. And then over here, right, we have this one is actually going to work out. This is 2 by 5, which is a factor of 10. So really, the main gist of this conversation is that you need to understand that when you're finding area, you've been looking at factors, you've been looking at factors that work to give you an area. When you multiply 2 numbers, those are factors. And so that's what we need to take away from this. Questions that you really need to understand is that 2 and 3 are both factors of 6, right? Because it makes that perfect rectangle there. 2 is a factor of both. 2 is a factor of both 6 and 10, because notice there and there, 2 is there. And so you notice that this works out every time it's used. 2 makes a perfect rectangle. 4 is not a factor of either 6 or 10. So 4 is not a factor, and here you see it, right? This is 1, 2, 3, 4, and that does not work for 10, and then here it does not work for 6. Also doesn't work this way either. So that's what you have to understand going into this, is that you could visibly see that those are not factors because they don't make a perfect rectangle. So we're going to move on to the next activity, which is called David's Bake Sale. In David's Bake Sale, we're going to be looking at combinations of packaging brownies and cookies. And so the goal here is to find all the possible combinations, but we're really thinking about what numbers multiply to give us, right, the brownies or the cookies. So we really have to think this through, right? And so we're going to go ahead and get started. So David is preparing brownies and cookies for a bake sale. He would like to make equal size bags for selling all of the 48 brownies and 64 cookies that he has. Organize your answer to each question so they can be followed by others. So how can David package all the 48 brownies so that each bag has the same number of them? How many bags can he make, and how many brownies will be in each bag? Find all possible ways to package the brownies. Well, I just told you that you're going to be asking yourself, what numbers multiply, right, to give me this 48? So I'm really thinking about, what are my factors of 48? What numbers, when multiplied together, will give me 48? Well, I'm going to start with my very basic. So I know that one bag could have 48 brownies, right? If I wanted to just sell brownies that way, I could. I could just put them in one bag and have 48 brownies. Or the other way to think about that is I could have 48 bags with one brownie. Now, maybe the 48 bags with one brownie might be a better way to sell, because if you're going to sell this way, most people aren't going to buy, 48 brownies in one bag. So it might be standard to do that. And then I have to think, 48 is an even number, and so I know that 48 is divisible by 2, so I could do 2 bags. And half of 48, right? So if I cut 48 in half, that's 24 brownies. So it could be that, right? Or it could be 24 brownies, or 24 bags with 2 brownies, right? It's just the way that we're looking at this. When I'm thinking about 48, right, I think, what's the next number that can go into it? Well, if I know my divisibility rules, divisibility is saying that if I add 2 numbers together and they give me a number that's divisible by 3, then that number is divisible by 3. 4 plus 8 is 12. 12 is divisible by 3, so I could do 3 bags. And now I have to think, how many, right? So if I have to check my work, 3 goes into 48, so I'm really dividing this, right? 3 can go to 4 one time, 3 can go to 18 6 times. And you should notice something that's happening here. So that's 16 brownies. Or you could have 16 bags with 3 brownies. The next number, 4, right? 4 goes into 48 because we know our multiplication vectors 1 through 12. 12 times 4 is 48. So I could do 4 bags with 12 brownies, or I could do 12 bags with 4 brownies. And then 5 does not go into this because when you're multiplying by 5, it's 5, 10, 15, 20. So there's a pattern there. It's either 5 or 0. So 5 doesn't go in. 6, well, I know 6 does go in, right? 6 times 8 is 48. 6 bags with 8 brownies. Or I could say 8 bags with 6 brownies. So that's for problem 1. So that's 1, 2, 3, 4, 5, 6, right? 6 different ways. If you think about the second way, then technically you're going to get 12 different combinations that they could have because it's just dependent on how you package them. The second question says, how can David package all the 64 cookies so that each bag has the same number of them? How many bags can he make and how many cookies will be in each bag? So really now we're looking at 64, right? So I want to package 64 cookies just like I did the brownies. So for the first one, right, it's 1 bag and 64 cookies, or 64 bags and 1 cookie. 64 is also an even number, so if I were to take that into account, cut 64 in half, I get 2 bags and half of 64, right? Half of 64 is 32, or 32 bags and 1 cookie. Now I'm going to go to 3. Remember, the divisibility rules for 3 states that if you add up the sum of the digits, right, 6 plus 4 makes 10. 10 is not divisible by 3, so 64 also is not divisible by 3. 4, I need to check 4. So 4, I can divide 64 by 4. 4 goes into 6 one time, and then you have 24. 4 goes into that 16 times, so 4 does work. So I can have 4 bags. And 16 cookies, or 16 bags. Oh, that's actually supposed to be 2 cookies. 4 bags and 16 cookies, or 16 bags and 4 cookies. And then 5 doesn't go into 64, so I have to move on. 6, if it's not both a factor of 2 and 3, then it's not a factor of 6. 7, if I know my multiplication tables of 7, 7 does not go into 64. 8 does, so 8 bags and 8 cookies. And then you can't redo that. So those are the possibilities for that one. So it says, how can David package all the 48 brownies and 64 cookies so that each bag has the same combination of items? How many bags can he make, and how many of each bag will be in each? How many of each will be in each bag? Find all possibles to both. Find all possible ways to package both items. Well, in this one, right, we're really thinking about numbers that go into both of these, right? And so when we're trying to package both of them, we need to think about both ways that are possible. So I want to look at my list and find numbers that I could package them at. So I know that I could package 1 bag with 48 brownies and 64 cookies, because 1 and themselves are a factor to give you that answer. Looking at the next number, I know I have 2 here and I have 2 there, so I could do 2 bags with 24 brownies and 32 cookies. The next numbers that they share in my list is I have, well, this one has 3, but the next one is 4. This one also has 4, so I could do 4 bags with 12 brownies and 16 cookies. The next number that they both share is 8. 8 goes into both of them. So 8 bags with 6 brownies and 4 cookies. No, and 8 cookies. My mind is not there. 8 bags with 6, because 8 times 6 is 48, 8 times 8 is 64. And then last but not least, they both do have 16. There's 16 here, and there's 16 here, so you could do 16 bags with 3 brownies and 4 cookies. So what is the largest number of combination bags that David can make with no leftover brownies and cookies? Explain how you know it's the largest possible answer. He can do 16 bags with 3 brownies and 4 cookies. Because 16 is the greatest common factor of 48 and 64. So that's really where we're trying to get to, is this understanding of the greatest common factor. So the largest number of combinations would be our GCF, which is known as our greatest common factor, and our greatest common factor is 16 because 16 goes into both 48 and 64. And normally, you could list out all the factors of both numbers. That's a strategy that we're going to use in the next example. So this is a way to approach this to begin with, and then we're going to move on to the next activity, which is this. So the greatest common factor, which is how we all learned it. So the greatest common factor of 30 and 18 is 6. What do you think the greatest common factor means? So the greatest common factor means it's the largest factor that the numbers share. Right? So when you're thinking about greatest common factor, you're thinking of the largest possible number that goes into both of the numbers that are given. So 6 is the largest number that both of these have. That is a factor of both of them. 6 times 3 is 18, 6 times 5 is 30, right? So both of them share the factor of 6, and that's the largest factor, or also the largest number that both of them share. But we're really thinking about the largest factor that both of them share. So we're going to do this to help you make sense of this. So find all the factors of 21 and 6, then identify the greatest common factor of 21 and 6. So my factors of 21, right? So I'm going to start by saying 1 and 21. This is odd, so I know 2 doesn't go in. 7 times 3 is 21, so 3, 7. And I'm pretty sure that's it. So those are factors of 21. For 6, I know 1 and 6. And I also know 2 and 3. Those are the factors of that. Now, looking at this list that I just made, I want you to find the greatest number that both of them share. Well, the greatest number that both of them share is 3. So the greatest common factor, the GCF, is 3. right? That's the greatest common factor that both of them have in their list. Find all the factors of 28 and 12, then identify the greatest common factor of 28 and 12. So factors of 28, again, we have 1 and we have 28. 28 is even, so 2, half of 28 would be 14. 3 does not, 8 plus 2 is 10, and so that does not go in. 4, well, I know 4 times 7 is 28, so 4 and 7 work. And that's it for that one. 12. 1 and 12, it's even, so 2 and 6. And then 2 plus 1 is 3, so 3 goes in. 3 times 4 works, and that's your factor. So now you're looking for the greatest common factor between those, and so the one that they share is 4. So the GCF is 4. The greatest common factor is 4. Okay, number 4 says a rectangular bulletin board is 12 inches tall and 27 inches wide. Henry plans to cover it with squares of colored paper that are all the same size. The paper squares come in different sizes. All of them have whole number inches for their side lengths. What is the side length of the largest square that Henry could use to cover the bulletin board completely without gaps or overlaps? So what we're going to do here is we're going to find the greatest common factors of both 12 and 27. So that's what I'm going to do for this strategy. 12, factors of 12, 1 and 12. And I just did this up top, 2 and 6, right? And 3 and 4. And then for 27, right? 1 and 27. 7 plus 2, so 9, 3 and 9. And then outside of that, that's basically it. That's whole numbers. So the one that they share, right, is 3. So the GCF is 3. The square is 3 inches wide. The square is 3 inches wide, and so that's because the square is 3 inches wide, which is your GCF, and then so I'm just thinking, explain or show your reasoning. You've done that there. How's the solution to this problem related to the greatest common factor? When finding the greatest possible solution, GCF is applicable. GCF is applicable. So when you're asked to find the largest combination of something, so this one here is asking about a rectangular bulletin board. You have this by this. They want perfect squares. And so perfect squares, right, mean that the side length of each one has to be the same size. And so the number that goes into both of those is 3. So 3 is a common factor of both 12 and 27, which is why it works in this problem. And so you're really just, when you're looking at this problem, you're thinking, what is a number that goes into both of those two things that will work for the situation? So that's what we're looking at for the greatest common factor. And then the exit ticket today says, what is the greatest common factor of 24 and 64? So we're going to list out factors of 24. So factors of 24, I know 1 and 24. Well, 2 goes into 24, so 2 and 12. 3 also goes into 24. 3 times 8. 4 goes into 24. 4 and 6. And I'm thinking higher than that. That's a possibility. 64. 1 and 64 are factors. 2 and 32 are factors. 3 doesn't go into that. 4, well, I know 4 and 16 are factors. And then 5 doesn't go in. 6 doesn't go in, 7 doesn't go in, 8 is a factor. And so I'm looking for the greatest common factor here of these two numbers. And so the greatest common factor between them seems to be 8. And so the GCF is 8. Which works there. In your own words, what is the greatest common factor of two whole numbers? How can you find it? The greatest common factor of two whole numbers is the largest number that divides evenly into both numbers. You can find the greatest common factor, you can find the GCF by listing the factors of each number and then finding the greatest one. That is the same for both numbers. Okay, so that's what we're looking at today. I appreciate you all for watching and subscribing, and of course, can't wait for us to learn today.